Just like in the case of the electric field, we could calculate the electric field created by a static distribution of charges. There is a way to calculate the magnetic field created by a steady electric current. This is the Biot-Savart law. The Biot-Savart law is a fundamental principle in electromagnetism that allows us to calculate the magnetic field generated by a current-carrying conductor at a given point in space, named after French physicists Jean-Baptiste Biot and Félix Savart, who developed it in the early 19th century. This law provides the means to determine the magnetic field due to any small element of current. They developed this law in 1820 based on the measurements of the magnetic field produced by electric current. In their experiments, Biot and Savart observed that the strength of the magnetic field generated by a current-carrying wire decreases with the distance from the wire. The field's magnitude is directly proportional to the amount of current, and the direction of the magnetic field allows a right-hand rule relative to the current direction. This law is especially used in calculating magnetic fields produced by currents with specific geometries, such as straight wires, loops, or solenoids. The Biot-Savart law highlights the following important characteristics of magnetic fields generated by currents. Magnitude dependency. The strength of the magnetic field is directly proportional to the current's magnitude. Distance dependency. The magnetic field decreases with the square of the distance from the current element. Direction of the field. The magnetic field vector is perpendicular to the plane formed by the current element and the position vector of the point where the field is being calculated, in accordance with the right-hand rule. For any infinitesimal segment of current-carrying wire, the magnetic field dB at point P in space due to a small current element dl carrying current I is given by dB is equals to mu naught over 4 pi I dl cross product r hat over r squared, where mu naught is the permeability of free space, a fundamental constant, which is mu naught is 4 pi times 10 to the power of negative 7 newtons ampere to negative 2. I is the current through the element. dl is a vector representing the direction length of the current element. R is the position vector from the current element on to point P. R hat is the unit vector in the direction of R vector, and this cross indicates the cross product. To find the total magnetic field B at a point due to a continuous current distribution, we integrate the contribution from each infinitesimal element along the conductor. B is the integral of mu naught over 4 pi, then I dl times r hat over r squared. This integral can be evaluated based on the specific geometry of the current-carrying conductor. Let's integrate Biot-Savart law for a specific case. Let us apply the Biot-Savart law to calculate the magnetic field at a point at distance a from a long straight wire carrying a current I. First, consider a segment of wire carrying current I. We want to calculate the magnetic field at point P located at a perpendicular distance a from the wire. Let the wire lie along the x-axis with P located at a distance a along the y-axis. For each small element, dl, along the wire, we can write dl is equals to dx I hat, where I hat is the unit vector along the x-axis. The distance from the element at x to point P is r is equals to square root of x squared plus a squared. Therefore, dB is mu naught over 4 pi, and then I dx I hat cross product r hat over r squared, where r hat is a unit vector pointing from dl to P. Now, let's be careful here when it is time to multiply I hat times r hat. This is a tricky part that can mess up our calculations of B. So let's go step by step. We can use our right hand to test this. If we point our fingers in the direction of the first vector, dl, and curve them in the direction of the second vector, r hat, we get that the magnetic field will point out of the screen at point P. But let's do the maths. Both vectors I hat and r hat have unit length. But this is a cross product and we need to be careful with the angle. Let's call phi to this angle and theta to this other one. Remember that I hat and r hat point in these directions. I hat cross product r hat is going to be the magnitude of these vectors, which is 1 times the sine of phi, and the sine of phi is the same as the cosine of theta. Putting this back into the differential of magnetic field dB, now we have several variables x, theta, and r. These three magnitudes depend on the position of the differential of length, so it is time to write them three in terms of only one of them. For that, let me write the trigonometric equations for the cosine and the tangent of theta. From the first one, 1 over r squared is, and I can differentiate the second one to find dx. dx equals to the differential of the tangent of theta. I skip a couple of steps here, but you should do them on your own to find that. dx is ad theta over cosine square of theta. Putting this back here, mu naught I over 4 pi times dx times 1 over r squared times the cosine of theta. This simplifies to mu naught I 4 pi cosine of theta over a d theta. Let's clear the blackboard. Now, for the magnetic field, I only need to integrate this expression. I will calculate the magnitude of the magnetic field first. I have to integrate along the whole current along the wire, which in this case goes from negative infinity to positive infinity. This is the same as integrating theta from negative pi over 2 to positive pi over 2. We could have written this in terms of the angle phi and then integrate from 0 to pi, and we should get the same result, of course. The integral of the cosine is the sine, so sine of pi over 2 is 1, and minus sine of negative pi over 2 is 1, so the magnetic field is mu naught over 2 pi a I. And remember that this points in the k hat direction. The symmetry of the setup shows that the magnetic field components along the wire cancel out, leaving only a circular component around the wire. Integrating along the length of the wire gives B is equals to mu naught I over 2 pi a. This result shows that the magnetic field at a distance a from a long straight conductor is directly proportional to the current and inversely proportional to the distance from the wire. This example demonstrates how to use Biot-Savart law to calculate the magnetic field at a point with symmetry considerations, simplifying the integration process. So, Biot-Savart law is essential for calculating magnetic fields due to arbitrary current distributions. By using this law, we can derive magnetic fields in various scenarios and predict the behavior of magnetic fields around currents with specific geometries. The example of a long straight wire demonstrates a practical application, highlighting the inverse relationship between distance and magnetic field strength. The Biot-Savart law not only provides a clear mathematical expression for these magnetic fields, but also serves as a bridge to understand more complex magnetic field configurations in devices such as coils, solenoids, and magnetic circuits, as we will see soon. Let me know your questions in the comments below, and may science be with you.